So we are discussing about the tool wear and tool life, and we are also into the variables that are affecting the tool life. Okay, till now we have seen these are the variables that are affecting the cutting conditions, tool geometry, and tool materials, work materials, as well as the type of cutting fluid and the cutting fluid application technique. Now we are discussing about the variables affecting the tool life. As you can see, these are the A to F are the variables that affects the cutting tool life. The cutting conditions, tool geometry, tool materials, workpiece materials, cutting fluid type, and its application techniques. There are various techniques. Okay. So till now we have seen three things, that is cutting conditions we have seen, tool geometry we have seen, and tool materials, different materials that are from HSS to diamond we have seen. Now we are going to see how various workpiece materials that will affect the tool life. Okay, so there are n number of materials. As the world progresses, we are coming across the variety of materials. So those are nothing but the workpiece materials. As the world grows, the advancement grows. We are coming up with various workpiece materials. If the workpiece material is harder, you need to take the tool materials also harder. Okay, so that's about the workpiece material. Now we will go into the workpiece materials. So there are variety of workpiece materials ranging from soft to hard to brittle to ductile. It is a overview slide where you can find many of the workpiece material. Brass, these two are not brass, but these are the brass workpiece material, copper workpiece material, and the gold. Normally I cannot say that do the machining operation, but some of the special cases one do the machining operation, such as to fabricate the car and all those things, and the silver and all. These are the overview of materials, and the world progresses, we come across with some of the biomaterials, ceramic materials and all those things. Anyhow, this is just an overview. We just go into the different materials that we come across. Okay, silicon carbide is one of the ceramic material. It is very difficult to machine the ceramics because these are the brittle materials and hard materials. Okay, these are two properties. These are brittle, and another one is these are hard materials. So because of this, it is very difficult to machine this material. Another advanced material is the titanium and its alloys. Okay, so the basic problem in machining of titanium is that it is a poor thermal conductor. Suppose if I want to machine this one, what will happen if it is a poor thermal conductor during the machining operation? If at all I want to cut the titanium, the chip is moving and it is a poor conductor. So the temperature stays in the machining region itself, and at the same time the temperature stays at the bottom of the chip. So the bottom of the chip gives the temperature to the workpiece. At the same time, the temperature that is staying on the workpiece also will impart to the tool. So the tool thermal softening will takes place at early stages. That is the one of the disadvantage, but the same is considered as an advantage in machining of aerospace alloys for turbine blades and all those things. If the temperature is stays on the surface, whenever the flight is traveling at a higher altitude, the air comes, and if the surface temperature is very high, that cold air will takes off the heat that is generated. That is one of the advantage. That's why mostly titanium and its alloys are used in two applications. One is biomedical application, another one is aerospace application. Okay, so these are the two applications normally. See, in aerospace, I already said the turbine components and all those things. If you come to the biomedical applications, normally titanium and the titanium alloys are considered to be the bio-inert materials, so they don't cause anything to the body. That's why some of the implants like knee implants, hip implants, these are all developed by the titanium. Anyhow, we will come across how these are machined and all those things in a big way, I mean to say in an elaborative way in upcoming classes. However, I will show you some of the glimpse just to the introducing of these materials in this class. Okay, so that's about the advancement of the materials. Okay, I can say these are the advanced materials. Okay, now coming to the ductile materials. The first variety of the workpiece materials are ductile materials. Normally, the ductile materials ranging from stainless steel. This is stainless steel only. This is the copper. Okay, so the stainless steel are the iron based steels. Okay, so machining this normally it generates the continuous chip. As you can see here, it generates the continuous chips. Most of the ductile materials generate continuous chip, because of which tool life. Because why we are studying? Because we are studying the effect of this workpiece material on the tool life. So, if a continuous chip is flowing on the rake surface of the tool, there will be a continuous heat going into the tool. At the same time, there is no vibrations because the system is continuous and the tool life will be good and all those things. The only problem with these materials is entanglement of these chips, and on the finishing region or the machining region is one of the problems. Okay, apart from it there is no much problem. That's why normally we have studied in the previous classes that continuous chip is good from the point of power consumption, because low power is consumed, at the same time surface finish point of view. But whenever this chip, if you see the figure number 2, if you see where the chip is entangled there itself. Okay, if the chip is entangled there, if it is slightly entangled on the finished surface, if you see this is the machined surface, this is the unmachined surface. Okay, so if the chip rubs against this one, what will happen? This will damage the surface finish of the workpiece. So I don't want this to be entangled. For that purpose, normally some chip breakers are used. So this is about the tool life. Okay, tool life will improve if we can use chip breaker for the continuous chip whenever we are machining the continuous. So whenever we are going to the brittle materials, ductile materials will give the continuous chip, but the brittle materials, normally the basic examples of the brittle materials is the cast iron. The first one, whenever we think about the brittle material, is the cast iron. Normally in short form we call it as a CI. So it will generate the discontinuous chips. Okay. The second is brass, and you can see the discontinuous chips. Discontinuous chips are lying on the lathe bed. Okay. So the one noting point that you can see here is on the tool life. The first I will speak about the tool life, and I will speak about some other thing about the cutting fluid also. I will come to the point cutting fluid later. Whenever we are machining these materials, tool life will be good. If at all you are machining a basic brittle materials like cast iron and brass, because these are not very hard materials. Normally if you go to the brittle materials like silicon carbide, alumina, titanium nitride, boron carbide, these are the very hard materials. So if you what all you are going for there, because of the interaction between these two, the hardness ratio, if you are maintaining the tool which is much harder than the workpiece that you are using, then there is no problem. Whenever you are going for the harder materials, then assume that I want to machine the Al2O3 or SiC, and still my cutting tool is coated carbide, then hardness ratio between two will be very less. Okay, the workpiece hardness to the tool hardness is very less. In that circumstances, the basic problem comes is tool wear will be high. Okay, so from the chip point of view, this is better. Discontinuous chips are coming, so it is obviously better. So there is no formation of continuous chip, and damaging of the final machined surface is not problem. Okay, so now my question to you is regarding the machining of the cast iron. There are some questions whenever you go to the interviews, because I faced this question when I was in my masters. Okay, so the question is that which type of cutting fluid that you will use when you are machining the cast iron. Okay, so let me answer this question. Normally cast iron will have high amount of carbon, and the carbon in the form of graphite. Okay, so the answer is just, it is a confusing answer whenever somebody asks about machining of the cast iron. So normally nobody, or minimally, you don't use the cutting fluids. The reason, I mean to say, cutting fluid is not used, just they might have asked to know the technicality of this process and all those things. Okay, so no cutting fluid will be used practically, but whenever the high depth of cut and high feed, if you are going, may be used. But normal conditions, whenever you are going for a low depth of cut and low feed rate, in that circumstances cast iron will have high percentage of carbon will be there. So carbon in the form of graphite. Okay, graphite, if you see nowadays people talks about graphene and all those things. So the graphite act as a self lubricant basically. Okay, so whenever you drill a hole in a cast iron, whenever you do machining, like if you see for example here, cast iron is machined here, so no cutting fluid is used, because the carbon content which is in the form of a graphite in the cast iron will act as a self lubricant. If I have already lubricant within the material, then I don't need to use additionally lubricant. Why I have to increase the product cost? So normally cutting fluids are not used whenever you are machining the cast iron. Okay, particularly because of the, it will act as a self lubricant. Okay, so another materials are hard materials. Hard materials, some of the brittle materials are also called as hard materials. But what I mean to say is, if you see hard materials, whenever you try to machine it, there is a lot of spark will come. So spark in terms of, you may say this, it looks like a fire that you can see in the video. See, the video shows the turning operation of hard steels. Okay, this is an experiment that done at our laboratory when I was studying. Hard steels are machined by the coated carbides. Since there is a hardness ratio is very less, at the same time the interaction forces are very high, because of which you can see the chips which are in terms of, the chips are like reddish chips are coming out. At the same time, if you see, the process stops like this. If a process stops like this, or if it is continuous, where you can see the chip is entangled there. Okay, so I am machining a hard material, but hardened steel. Steel is a ductile material. Okay, so ductile material is giving us the continuous chip. Since I am using moderate depth of cut and feed at the moderate speeds, so red color chips are coming out, which is very dangerous from the point of operator as well as from the point of tool wear also. At the same time, chip is entangled there in the machining region. If you see, the chip is entangled there in the machining region, which imparts some more and more temperature onto the rake surface of the tool. Okay, so this causes, or this reduces drastically the tool life. Okay, Okay, so this is the basic problem whenever you machine the hard materials. Okay, this is about the turning process. Normally, this is what the turning process, turning of hard materials. This is the milling. This process I will go in future, and I am going to talk about this one. Same phenomena you can see there also. If at all normal milling is done where the cast iron or something, this won't come. But whenever you are going to use very hard workpiece materials, normally hard, this is another one statement is there, that is called hard turning. Okay. Okay, normally people say hard turning. Hard turning is where the workpiece hardness is above 50 HRC. Normally 50 HRC, that is Rockwell hardness scale C. It can be some of the textbooks they refer it is 54. Some people they refer there is a correlation between the speeds and hardness. Some of the textbooks they say that it is above 60. Okay, normally for the basic introduction purpose you can assume that if you are going to machine a workpiece material whose hardness is above 50 HRC, normally you can call it as a hard machining, but 50 plus or minus 5. Okay, so it can be, I cannot say minus, I can say only plus. So this is about the machining of the hard materials. Now we come to the machining of biomaterials. Okay, so the basic purpose here is a material, you have seen the hard materials, you have seen the soft materials, and you have seen the ductile and hard materials and all those things. Whenever you are going for the implant materials like hip implant or knee implant and all those things, first you see is whether the material is biocompatible or not, or whether it is a bio-inert or not. You cannot use straight away mild steel or cast iron as a bio-implant material. So normally these materials are hard materials. Okay, basically these are biocompatible materials with slightly hardness, and either it can be bio-inert also. Okay, so if you see the implant material where is a hip implant is placed here. So how to fabricate this one? This hip implant will have many components like femoral stem is there, femoral head is there, some plastic or the synthetic liner is there, at the same time acetabular socket is there. Okay. So these are the different components that are assembled and form a hip implant. Okay, so now how to machine this one? It is a big challenge because machining of the femoral stem is different process, femoral head is a different process, acetabular socket will be a different process. Normally this femoral head and femoral stem can be disassembled also, because this can be manufactured by different process. Normally machining, finishing and all those things will take place. Okay, so why I am emphasizing about the machining of these things is this, if at all like you have seen hard machining, if there is a high temperature generation during the machining operation, the basic problem comes is its metallurgical properties goes bad, its surface integrity goes bad. Okay, what do you mean by surface integrity? Okay, so surface roughness plus surface metallurgy combinedly called as a surface integrity, because whenever I do the machining operation, I want to retain the basic properties of the parent material. Okay, that is my objective. But if you see like previous video where the firing is there and all those things, when there will be a temperature effect on the workpiece, if that is the case, normally the femoral stem, that normally if you see the femoral stem, this is machined and different stems are there. So the basic stem, if you see the first one, This is basically machined by the milling process. If you the milling process is like previous one where that fire chips, red color chips are going, then the metallurgical aspects of the this will go bad. So I don't want that. For that purpose I have to machine with a good tools. At the same time I have to choose my machining conditions properly, so that my surface roughness what I will get is better. As you can see in the two, the surface roughness should be better, it is shining and all those things, and it should give you a property where whether I want it super hydrophilic property or super hydrophobic property and all those things, that's depend on. Normally I require hydrophilic property so that I can coat the biomaterials on it, as well as whenever you implant in it, the cells will grow on it. Okay, so for that purpose, normally you do a safe machining process. Okay, that about the stem. So you can see on the three, normally coating is there. So different people will coat at different locations. These are the bioceramic coatings are there. Okay, different companies will quote on the different. Okay, we are not talking about the coating, but anyhow why I am talking about the coating is I have to mesh such a way that I have to get the proper surface roughness. If I have the proper surface roughness, then my fluid, my the surface wettability I will get properly, and the surface wettability is decides my contact angle. That surface wettability itself is a contact angle, so it will decides the coating, effective coating and all those things. Another one is surface metallurgy. As I said, surface integrity is nothing but the surface roughness and surface metallurgy. Okay, if I don't heat or the hot chips are not coming, that means that my surface of my product will have better surface roughness and surface metallurgy. Both things will be very good. Okay, so these are both are required. Okay, then I can call it as surface integrity. Okay, this is about the machining of the femoral stem. Okay, so now we will see how the femoral head is machined. This also used by the milling process only. Normally CNC milling people will use for the femoral head. The femoral head is differently machined, then it will be assembled. Normally the femoral head whatever the machined here will be assembled on the this one, so it will come and occupy like this, as you can see in the this picture. Okay, so this is about the femoral head, and the most complicated is internal machining of the acetabular socket. Okay, or acetabular component. Some people they say acetabular component. Now people are saying the acetabular socket. Okay, some people they say that acetabular cup also they will say. So this is also difficult to machine because you have to machine internally. Nowadays advanced techniques are there, so you can machine it. Now the tool, so acetabular socket and acetabular femoral head, acetabular head or femoral head will have to assemble properly. For that purpose machining is properly done, and the surface finish should be as minimum as possible. Then only, these are all called ball and socket joint. Whenever the ball will go into the socket, if the surface roughness is good, then the flexibility or the rotation will be easy and all those things. So machining of these things is most important because you have to maintain proper surface roughness in the range of nanometers. For that purpose people will do the machining operation followed by the polishing operation, and some people they are also using the liners. So the still hard liners are used inside the acetabular socket. So those machining that I am not talking about here, but the machining of those liners also will be difficult. Okay, so surface should be properly maintained. If you come to the another one material. Normally, nowadays people are moving towards the polymer based implants and all those things. But however, as a mechanical engineer, and the most important things, two widely used important things are hip joint and knee joints. That's why I am talking about the machining of knee joint and hip joint and all those things. If you see the knee joint, normally whenever the knees goes bad, then the total knee replacement is done. So artificial cartilage will be there at the middle. Normally this is cartilage or the meniscus. People say this is the knee implant. Okay, so if you see the knee implant required very good machining properties. Okay, normally this is machined by the simple processes like milling only. Okay, so you can see how the milling operation is taking place on the. So there are different varieties of knee implants are there. These knee implants are machined, and you can see in the zoom version how these are machined. This is the another version of the knee implants. There are different knee implants. These are done by the milling operation. You can see here, okay, in the zoomed version. So what I want to emphasize here is whenever you are machining the biomaterials. So there are two varieties of common materials that are used. One is chromium, cobalt, iron based and titanium alloy based. Okay, so these are the two varieties that are used, that is Ti6Al 4V is one of the titanium alloy, but chromium cobalt iron is one of the common material. So these are the two materials. Whenever you machine these two materials, you should take care about the temperature should not go beyond what it has to go. Otherwise, the metallurgical layers will form, metallurgical deterioration will take place on the surface of this one, which we don't want. And the surface roughness also should be maintained properly. For that purpose, there are the post processings are there, not only the milling, but the basic process that one has to make sure that it should be in a good shape, and good surface roughness should be that at the machining. Okay, if you are machining, you have to use advanced tools. At the same time, you should take care that the tool wear should be as minimum as possible, so that you will get proper roughness, proper metallurgy on the workpiece. Okay, so now we move to the some of the other materials like elastomers. Just I will give you the glimpse. Since we are talking about the biomaterials, there are so much polymers coming into the market where the machining is taking place. For example, the machining of internal fixation devices that we are doing, that internal fixation devices like cortical screw, bone screws and cortical pins and staples and all those things, these are to be machined. Whenever you have to machine these things, these are all viscoelastic materials and it is very difficult to machine it. So some people goes for 3D printing also. Okay, so whenever you do the machining, if it is elastomers and all those things, it has its own drawbacks, because if I give certain depth of cut, because of the elasticity of the workpiece material, it may deform. Some material may come in the particular depth of cut, some material may not come. If I am giving 5 microns, the cut may be 4.5 or something, there will be some deformation will takes place and all those things. Okay, so some of the components that are shown here where the elastomers or the plastics are used, things like is some of the small components are given which are made up of plastics. Okay, so in combination with this, what I want to say to you is, if at all we want to cut the small biomaterials, polymer biomaterials, because this is just a basic, but the application of these pictures is, if I want to cut a polymer based biomaterials like bone screws, PLA, polylactic acid is the one of the thing, PEG. These are the some of the polymers nowadays coming up which are used in the human bodies. if at all I want to cut a component, or if I want to cut a simple screws or pins for biodegradable pins, it is this knowledge of machining of the plastics, machining of the elastomers will help a lot. Okay, this shows simple, but however the application is enormous in terms of bio applications, as well as some of the components you will use in automobiles and all those things. Okay, now move forward to the different materials, that is called ceramic materials. Ceramic materials can be machined by, normally if it is a soft ceramic, like hardness is not that much big, or if it is done by the powder metallurgy technique, normally the ceramic components are done by the powder metallurgy technique. Whenever I want to do the machining operation of this one, you can do it by giving the low depth of cut and low feed rate and all those things. But commonly used methods are heat assisted methods. Normally if you see, these are all heat assisted techniques. Whenever I want to machine it, what I will do is I just apply a heat, then I will do the machining operation. This is called hot machining of ceramics, or another way of mentioning is, this is called hot machining. Or some people also call it as a ductile regime machining. Machining of brittle materials. Okay, so what I mean to say is ductile regime machining of brittle materials. Okay, if you see this one, I will just explain you what it is. Ductile regime machining of brittle material. That means I have a brittle material here. This is a brittle material which is the initial stage of the workpiece. Now I have to convert into the ductile mode, then I have to machine it. That is what it says. Okay, I have a brittle material, I have to convert into the ductile material, then I have to machine it. For that purpose, I have a brittle material and I am using a heat source by induction heating or laser beam heating and all those things. I am converting into the ductile mode, then I am machining it. Okay, so I will show you a picture where you can clearly understand what I want to specify from the point of ductile regime machining of brittle materials. You can see here laser assisted machining of ceramics. Okay, so I have a workpiece material. This is the workpiece. The tool is cutting from the other side. Okay, this is the laser source. This is the laser. So laser beam is falling here. You can see in this machining region. So workpiece is a ceramic, laser is falling from the top, and the bottom there is some support. If the laser falls sideways or something, it should not fall on the lathe bed or something. For that there will be support and the machining is taking place. Okay, what here is basically the material is a brittle material. And because of the heat, that region converts into ductile, then machining is taking place. Okay, so material is a brittle material because of the laser beam, which is a high temperature beam. But I am not saying that laser is very high or something. The laser, that one has to use the laser power accordingly, so that it will convert into the ductile regime according to the material basically, and you have to do the machining operation. Okay, this is about the ductile regime machining of brittle materials. One of the examples is laser assisted machining. So now the variables we have covered is A to D we have covered, and next one is the type of cutting fluid. As we see our course as machining fluids, and we come elaboratively about the cutting fluids in upcoming classes. However, just a slight glimpse I will give to you. So the cutting fluids basic function, if you see that it reduces the friction and wear and cools the cutting zone, that is nothing but cooling and lubrication. This is called as lubrication. And this is nothing but cooling. So two primary functions of cutting fluid is cooling and lubrication. That is what I mean to say from the first 2 points. Wash away chips because there should not be any entanglement or sticking to the surface. So wash away the chips. Normally this word comes in terms of drilling operation. So prevent corrosion. So in order to prevent corrosion, it will have a lot of corrosion inhibitors and all those things that will help the cutting fluid. Reduces the forces and energy consumption. Normally lubrication will help from the point of reducing the forces. We have seen already power consumption equal to Fc into V. So cutting force, if the lubrication is there, proper lubrication is there, the cutting force will be minimized or reduced. If the cutting force reduces, normally the power requirement goes down. That is about the cutting fluids. So now cooling properties. Normally if at all I want the cooling properties, in a dominating cooling properties, waters used to be as a coolant type, basic coolant type. Normally the cooling variety of cutting fluids are used in high speed applications, because high speed applications temperature generation will be high, so you have to take out that whatever the heat developed due to the temperature and all those things. For that purpose, cooling dominating cutting fluids are used. The most effective tool material that can susceptible to is HSS. Tool material susceptible for temperature failures is HSS. That means that the HSS cannot sustain for higher temperature. Normally in the previous classes when we were talking about the HSS, the basic drawback of high speed steel is its hardness. The hardness at elevated temperatures is low. That is a problem. Okay. So it is a tough material. It can take the impacts, but hardness is low. Okay. So the lubricants, normally lubrication dominate in cutting fluids usually are oil based fluids. Now what I mean to say is that coolant based are dominating cooling properties and lubricant based are dominated by the lubricating. That means that friction reducing agents. Okay. Most effective are the lower cutting speeds. Normally lower cutting speeds abrasion will be more. So at lower cutting speeds, friction and abrasion will be very high. For there, the lubrication is required. For that purpose, normally lubricant based cutting fluids are used. Also reduces the temperature and the operation. If the friction is reduced, partially you can reduce also the temperature. Okay. So this is another function. If you see already the lubricating properties and all those things, anyhow this graph we will see in the whenever we are talking about the cutting fluids and all those things. Still, since we have seen already the cooling properties and the lubricating properties, so if at all I want the better cooling property, water is the better cooling property. At the same time, if at all I want the better lubricating property, oils, mineral oils or petroleum oils are very good. Okay. So I want partially lubricating properties but dominating cooling properties, then I will use some water with some of the additives. Now I can go even for lean emulsions. Okay, emulsions are nothing but whenever we mix two fluids, normally this will become the emulsions. These are the other one. Commonly used, if at all I want to go for the better lubrication and low cooling properties, that's what I was talking about. Mineral oil with additives can be used. So the most of the time the commonly used are emulsions. Okay, so that I can have optimum cooling properties and optimum lubricating properties. For that purpose, emulsions will be used. If at all I want to add some of the additives like biocides, rust inhibitors, and are is also called as corrosion inhibitors. Okay, both are same. So high pressure additives, many additives are there that you can add to the emulsions. Okay, this is about the differentiation or the plot between lubricating properties of the cutting fluid to the cooling properties of the cutting fluid. Okay, so there are varieties of cutting fluids. Four basic styles are there. One is straight oils and synthetic fluids, soluble oils and semi synthetic fluids. These are the four varieties. Okay, synthetic fluids are not the naturally occurring one, but these are prepared in the laboratory. These are called as a synthetic fluid. Soluble oil, soluble with the water and all those things. Semi synthetic, some of the things are naturally taken, some of the things are developed at the laboratory and all those things. These are the basic categories which you can find old textbooks and all those things. Okay, whenever we want to go for the advanced versions, these are the advanced version of the cutting fluids. If you see, the first and foremost is a cryogenic cutting fluid. Normally cryogenic cutting fluid is nothing but a liquid nitrogen based fluid. This is basically used for high temperature applications, wherever if at all the titanium is machined or ceramic materials are machined and all those things. See here the temperature goes minus 160 degrees and all those things. Okay, this is about the cryogenic fluids. Cryogenic, whenever you, in the next slide I will show you how the cryogenic fluid is used and all those things. That's why I am not talking about much about this cryogenic fluid here. So the second variety is solid lubricants. Solid lubricants, it cannot be a big solid or something. Normally these solid lubricants are the solid nanoparticles or microparticles. You just mix with the externally mixing or internally mixing the air, and you can send to the machining zone. That is nothing but you have a, normally these are MOS2 and CAF2, sorry it is subscript, you can see here. So MOS2, CAF2, that is calcium fluoride and tungsten disulfide. So these are the common lubricating properties, even graphite also. Just you make a powder of this, which are the lubricating properties, and you send along with the highly compressed air. So this jet of air along with solid lubricants will go into the machining zone and it will help in the lubrication. Okay, the noting point here is the cooling properties of this one will be very low. This will help in terms of lubrication, so it will reduce the friction in the machining region. Okay, that's about the solid lubricants. Nanofluids is taking up in an enormous way. The nanofluids are nothing but you have the cutting fluid with you and you have the particles. Some of the people are using copper nanoparticles or copper microparticles. Some of the people are using Al2O3 ceramic particles. Some of the people are using MOS solid lubricants. Okay, what they are doing is they are taking a cutting fluid, they are taking the nanoparticles, they are mixing it and they are sending. Okay, so the beauty about it is, if you take the cutting fluid and assume that you are adding a MOS2 to it. Okay, so you have to check before that what is the chemical compatibility and all those things, and you make a nanofluid. Assume that I have a two things, cutting fluid is there plus MOS2 is there. So I am mixing and I am sending with high pressure. What will happen? The density of particles is very high compared to my fluid. So there is a tendency that in the chip tool interface, the particles will go and occupy this interior regions, so that it may help in the lubrication also. At the same time, it may try to lift by some of the nanometers or something. That is what some of the hypothesis people says and all those things. Some people they will use ceramic particles, some people they will use metal particles also. They have their own analogy in terms of these are the nanofluids. Term came from the refrigeration and air conditioning. Nowadays it is more relevant to the cutting fluids and all those things. Okay, this is about the nanofluids. So ionic liquids as a cutting fluids, this is one of the recently seen papers where the ionic liquids are also used as the cutting fluids, but mostly these ionic liquids are used for the lubrication purpose. These are very good lubricating. So most of the papers of this cutting ionic fluids as lubricants in tribological aspects, as well as you can also see in the metal forming and wherever the lubrication is required. Okay, so tribology and lubrication applications, ionic fluids are used. So people are bringing this and they are mixing with compatible liquids, cooling liquids such as water and all those things, and they are using it. The another variety is eco-friendly cutting fluids. Normally some of the people are using vegetable oil based and all those things. Eco-friendly cutting fluids are some of the vegetable oils or the mixture of vegetable oils. Since is cutting fluids, the petroleum based cutting fluids like straight oils or synthetic oils causes lot of problems whenever the emissions comes. So anyhow you will see in deep in the upcoming slide. So this causes a lot of problems. So in order to avoid all these things, vegetable oil based cutting fluids are used. Okay, so I was talking about to you on the cryogenic cutting fluids, but the cryogenic cutting fluid, the first one, just let me come back in the next slide about the cryogenic cutting fluid. Okay, this is about how we do the machining operation using the cryogenic. Okay, so normally used is liquid nitrogen. In the current photograph, whatever you can see is the liquid nitrogen based cryogenic machining, where the cryogenic fluid is as a coolant. Basically it is a better coolant because the temperature is minus 164 degrees. Normally minus 160 degrees is the temperature, so it is a better cooling agent. Okay, so applicable for high speed machining. Normally applicable for high speed machining or machining of the titanium and all those things, because the temperature stays on the surface itself. That's why these are used there. Okay, so the basic problem about this cryogenic is, if you don't protect the base or the lathe bed and all those things, if it falls minus 164 degrees or minus 160 degrees, fluid whenever continuously falls on the lathe bed, the lathe wherever the component or it falls, it makes it completely brittle. So you should be very careful, that the operator should be completely careful, because his hands or any body part should not come in contact with it, because it is dangerous. At the same time, the lathe other parts also should be protected apart from workpiece and tool. Okay, and especially from the machining region. Apart from these, everything should be protected. If you can protect, then this is a good process